Next section. In our class, we combined these two kind of together, gravitation and circular motion. The one that most people don't like. And I told you at the time, you weren't going to like it. When things start moving in circles or spinning, that's where physics gets a lot tougher. Let's start off with gravitation, mostly because it gives us one of those forces that it's kind of easy to keep track of. Big equation for this is force of gravity. Notice the big G, because this is how I kept them separate, where we're dealing with universal gravitation. It is G, the universal gravitational constant, which is something like 6.67 times 10 to the negative 11th. And then there are units that make it work out. It's Newton times meter squared per kilogram squared. But times the mass of object 1, the mass of object 2, divided by r squared. Now I'm going to remind you that sometimes this r is actually a radius, but this r means the distance between the two objects. What two objects? The two objects that you're trying to find the force of gravity between. The objects that have mass 1 and the object that has mass 2. Those are your two objects. However far apart they are, that is the number you put in there. You don't divide it by 2, you don't do anything else to it. It's the distance between those two. Now, when you have one object orbiting another, say we've got the sun here, and we've got the Earth going around it, we often see that as a circle. It turns out that the distance between those two is, in fact, it happens to be the radius of a circle. That is not always the case, though it is often. But it is important to remember that that is the distance between the two objects. Don't try and divide it by 2 or anything like that. Always ask yourself, what is the distance between them? That's the number that goes there. All right, so now on to the, because that's the main equation that we have for gravitation. There's one very similar where you get the potential energy from gravity where it's a negative of this and it's just over r. We talked about that briefly, but it's not something that we'll be focusing on too much. Doesn't hurt to double check it, but this is the main thing for gravity to take a look at least equation-wise. The next thing is circular motion. Most important equation on that, of course, is our centripetal force, which is mv squared over r. Where in this case, we have the mass of the object moving in a circle. Remember, everything that's going on here is describing the thing that's going in a circle. So you want to use its mass, how fast it's going, its velocity. And in this case, because it is in fact moving in a circle, this is the radius of a circle. That's why I said you'll often be setting this equal to that. And we're going to talk about that a little bit more in just a moment. Are they doing jumping jacks upstairs? All right. Now, the most important caveat to this is our centripetal force. Anything moving in a circle must have a centripetal force. And more importantly, in a more functional way, anything moving in a circle, my sum of forces has to be equal to my centripetal force. When I add up all the different forces acting on it, all of them, they all have to add up such that they are pulling in just the right way to make the thing move in a circle. If they don't, then the thing isn't going to move in a circle. Okay? It will continue to try and move in a straight line. A circle is not something that things naturally move in. They have to be pulled into it. By Newton's first law of motion, things will continue moving in a straight line unless they are acted upon. So you want them to go in a circle, you've got to act on them so that they don't go in a straight line. Seriously, jumping jacks. All right. This is the key to actually being able to apply that centripetal force. You will add up all of your forces, and all of them must be equal to this mv squared over r, where m is the mass of the object moving in a circle, v is how fast it's moving in that circle, and r is the radius of said circle. Okay, now remember, and this is one of the big things on this, a centripetal force is not an actual force itself. It only describes other forces. When you draw a free body diagram like we saw last time, you will not have a simple arrow that just says centripetal force. You will have an arrow that says something like force of gravity, because it's gravity that is pulling the thing in the circle. Let's say the moon going around the Earth. If I have the Earth in the middle here and the moon going around in a circle, it is the force of gravity that is physically pulling the moon in that circle. Taking a look at that, we would see that the free body diagram for the moon, so if I were to draw the Earth here, in fact I'll go ahead and do that, and we have the moon out here, and it's going in a circle, a very poorly drawn circle. If I were to draw a free body diagram at the exact point that I have listed here for the moon, I would have the force of gravity off to the left. It's being pulled on by the Earth, right? And then I would do my sum of forces. I would say that my sum of forces in the x equals negative force of gravity equals mv squared over r. And I would go through, I would plug in my equation for gravity like we saw up here. I would keep track of the fact that this negative means that it's pointed off to the left. It turns out that our centripetal acceleration is also pointed to the left, so our negative will most likely drop out. But I would go through, and this is how I would apply it. I would not mark this as simply my centripetal force, because centripetal force only describes a real force. I could swing something around, like my name tag or something, and it's the tension in that that is supplying the force for my ID card to go in a circle. If I cut that string, no more tension, no more force, my ID card just goes flying off in a straight line. Centripetal force only describes other real forces. Anything moving in a circle, all of those forces are going to add up to be our centripetal force, because that is the only way it can move in a circle. And I cannot stress this enough. Anytime you see anything moving in a circle ever, the sum of its forces are going to come up to that centripetal force. That is the only way that it can move in a circle. Always remember that. So when you see a charged particle moving through a magnetic field, lock on to the fact that you see it moving in a circle, because that means the force acting on it can be set equal to your centripetal force. That will be the key to solving any of these circle-based problems. Finally, one of the last things that I want to talk about with this, because it was kind of useful, and this kind of undermines one of the previous points I made. For things moving in a circle, they end up with a constant velocity, this v squared. Whenever they're in a perfect circle, for the most part, their velocity doesn't change. The acceleration is just making them change direction. So I should say their speed stays the same, but their velocity is constantly changing. In the end, in this equation, our value for v isn't actually changing. Because our velocity itself isn't actually changing, that means our acceleration is equal to 0. That old kinematic equation, we can now actually use delta x, v equals delta x over t. V equals delta x over t. The reason that I bring this up, and I even wrote a capital T like a foolish person, is for where I'm going. You can find the velocity of something going around in a circle by taking its delta x, the total distance that it goes, which is 2 pi r, the circumference of that circle, divided by the time it takes, its period. We use that to great effect to find our velocity here for our centripetal force and so forth. We ended up using this often in things like finding how fast the International Space Station would move. Now, one of the final things that I want to say, and it's conceptual about gravity itself, and we can go through and we can look at the equations if you'd like, again. But you can also take a look at Kepler's third law, and you'll find for a given orbital body, so if we're talking about the Sun or the Earth or anything like that, if you put a satellite in orbit of it, the period, and thereby the velocity that it's going, will change based only on how far it is from the star or the body. So if I have it moving out here, it's going to move much slower. This is completely independent of the mass of your orbiting body. Partly you can remember this by thinking of our solar system. Mercury, really tiny mass, spins around really fast here in the middle. That's fine. We get a little bit heavier for Earth and Venus, and they go a bit slower. But then we get really heavy back out here, and we have Jupiter going slowly. So you might think, well, maybe there's some mass related to that. But if you go way out to Pluto, which is even less massive than Mercury, it goes even slower than all of them. It doesn't matter what the mass is. All that matters is how far you are from that central body. The further out you are, the slower you have to go. Okay? So keep that in mind. Kepler's third law embodied that, where there was a direct relationship between the period squared was directly related, I shouldn't do equal, but to the radius cubed, the distance between the two. Technically it was the semi-major axis, but for most planets we're pretty much fine. So when you're talking about satellites in orbit of something, again, doesn't matter how massive that satellite is, all that matters is how far it is from the body that it's orbiting. Okay?